Hi, and welcome to another video in this series about big integers. In the previous episodes, I discussed addition, subtraction, and multiplication. Today it's time to tackle division. There is a reason why division comes last. Algorithmically, it is by far the most challenging operation. Addition and subtraction were straightforward. And the naive multiplication I implemented, well, it's called naive for a reason, but it still works and is good enough in some use cases. Division is different. Take schoolbook division. At every step, you actually divide by a single-digit number and multiply by a multi-digit number. It involves a lot of things happening at once in your brain as you look for the largest single-digit number such that the product is less than the current subset of the dividend. If I were to implement this in code, I would be facing several issues. First, and most importantly, I can't divide by a multi-digit number. In code, the equivalent of a digit is a word. I can divide a two-word number by a one-word number, but I can't divide by a three-word number. No way. When I say I can't, it means I would have to write code to make it happen. Mimicking what I do in my brain, there would be an iterative process that does long multiplication, evaluates the result, and adjusts. I could do that. I already implemented long multiplication, but just imagine how slow this would be. A loop of long multiplications wrapped inside another loop. There is no easy solution. If there were, we wouldn't be here. Fortunately, very smart people have done it before. So I decided to implement Donald Knuth's Algorithm D, as described in the Art of Computer Programming, Volume 2. It was first published in the late 60s, which commands immense respect for the author. I spent a lot of time debugging, and I must say that no AI was able to pinpoint the bug I eventually found myself, bringing great satisfaction. I'll be using a lot of the analogy between a decimal digit and a 64-bit word. Algorithm D only needs the ability to divide a two-digit number by a single-digit number, which I can do using unsigned int 128. I need to pause here for a disclaimer. ARM64 does not support such division in hardware, so the compiler will generate a software emulation, probably using a Knuth-like algorithm itself. On the other hand, it does perform multiplication of two 64-bit numbers very efficiently. And x86-64 handles long division in a single div instruction. Keeping that in mind, I will focus on implementing the algorithm, and I'll probably revisit this later. End of disclaimer. I will try to explain how Knuth's algorithm works without going into minute details, but still enough to understand the idea. I'll reuse the numeric example we had for multiplication. So now 27,950 divided by 325 equals 86. We are looking for an estimator that we call Q hat of the first digit of the quotient. A simple estimator could be 27 divided by 3, which gives 9, and which is close to the actual value of 8. But how good is this estimator? In the worst case, how far can it be off? When a dividend starts with 27 and the divisor starts with 3, q hat can be anything from 6 to 9. This is not a general solution, I'm just sticking to my example. Can we do better? Knuth says yes, by normalizing the divisor and the dividend. Normalization is very simple. You want the first digit of the divisor to be as large as possible. Knuth proves that if it is at least 5, then the estimate is off by at most 2. So normalization means multiplying both the dividend and the divisor by the same factor, which is 3 in my example, and you can see that the estimation error is reduced. In the binary world, normalization means ensuring that there are no leading zeros in the divisor. A left shift achieves this quite efficiently. But wait, I haven't implemented shift operators yet for class longer. Well, actually I have, but there is a nuance. If V has a full leading word, which is nil, we don't want to shift by 64 bits, because that would add an extra unnecessary limb to both operands and will probably break the algorithm. If I used my existing utility functions, I would trim the leading limbs, get the number of leading zeros, which is now strictly less than 64, and shift left. I rather decided to write a purpose-built normalize function, which is more efficient as it allocates only once and does only what it needs to do. So this is how I normalize V. I use the shift operator to normalize U, but I also trim, because U may have leading 0 limbs, which we never checked. Now I can set the size of the divisor, n, and m, which is the size of the dividend minus n. The algorithm sets them at the very beginning, but as I have trimmed, potentially, I'm doing it now. There are 2 loops. The outer loop on j goes downward from m to 0. The first step is to estimate q hat. Let me go back to the numeric example. At this step, 83 divided by 9 makes 9, but since q hat may overestimate the true value of q, we look at the next digits and do some math to check whether this is the case. There is proof that we don't need to compute q hat times the whole divisor, which would be expensive. Instead, we can perform much simpler single-digit operations. In my example, q hat must be reduced to 8. Remember, this correction is performed at most 2 times. Next, the inner loop multiplies q hat by the divisor and subtracts the product from un. The loop performs limb-by-limb multiplication and subtracts directly from un while tracking borrows. So now un contains 5850, and the next outer loop iteration can start. This time q hat is correct immediately, there is no adjustment, and we proceed to step D4. The remainder is 0, and when you look at the code, There is certainly more to it, but the extra code is mostly there to handle edge cases. The main takeaway is that the algorithm only does single-digit math and sometimes 2-by-1 digit division, and the multi-limb multiplication, which is expensive, happens only once per outer loop iteration. But still, no doubt there is a lot going on here, and the computational complexity of this algorithm is O of n times m, where n and m are the sizes of the operands. Now let's look at a few implementation details. Before calling Knuth divide, I check several edge cases to ensure that we are within the algorithm's prerequisites. I use int 128 a lot, for example, to aggregate two limbs into one, and to ensure that intermediate results don't overflow. But I also did something new this time. Instead of using shifts and casts to split a 128-bit value into low and high parts, I used a union, like this. Members of a union share the same address and provide simply a different representation of the same data. I also use intrinsics to get precise control over the borrow. And so far, I did not try any further optimization for several reasons. Because the algorithm is tricky and easy to break. The compiler's optimization are hard to beat, and the loops are tight and optimizer friendly. There are at least 4 temporary longer variables, so 4 allocations we can't avoid, plus a lot of code. So the marginal benefit of micro optimizations is very limited, though maybe not zero. I will look into some of those, including the 128-bit division. Let's briefly discuss some helper functions. Is0 is straightforward, but pay attention to testing where the body is empty. Leading 0 bits is quite easy and efficient thanks to this thing, which should compile into a single ARM64 instruction. Divide by UN64 handles division by a single-digit number, which doesn't fit Knuth's prerequisites. And finally, the shift operators, which deserve a few words, because there is a design choice. Either perform the exact shift in a single loop, or do a word shift first, and then a bit shift. And I took the latter path. Shifting by n bits can be decomposed into full words plus remaining bits. First, I shift entire 64-bit words. In a right shift, the least significant limbs are discarded. Then each remaining word is split into the part that stays in the same limb and the part that moves into the next limb, with leading bits padded with zeros. Left shift is similar, except that it allows the number to grow. I believe that there is an advantage to doing this in 2 steps, because the full word shift can be implemented as a mem move or something else which is optimized into a mem move, which is insanely fast on Apple Silicon thanks to vectorization and other tricks. So it isn't even a loop per se. The second step, where we do have a loop, well, it is a tight loop. It is optimizer and cache friendly. And finally, it's easier to move everything in place without temporary arrays. Note that the direction of the loop avoids overwriting data that is still needed. That said, shifting is still expensive, and there are strategies to mitigate that, but that's a major design change. Okay, that's it for today. Remember, the link to the Git repository is in the description. See you next time, and thanks very much for watching.